Let's say we're at a point x1, y1 in the Cartesian plane, and we want to get to a point x2, y2 taking the shortest possible path. To figure out the length of this path, we could construct a right triangle where the hypotenuse is equal to the line segment between the 2 points, and where the length of the legs of this triangle are equal to the difference in our x values and the difference in our y values. Then we could use the Pythagorean theorem to calculate the length of the hypotenuse. However, what if we were in a non-Euclidean geometry where we couldn't move diagonally? What if we could only move parallel to the x and y axes? We could think of it as if we were on an infinitely fine grid, where we can turn wherever we want, but we can only ever make 90-degree turns, and we can only ever be moving vertically or horizontally. What would our shortest path be then? Clearly, if we ever move in the opposite horizontal direction as our new point, we're going to unnecessarily add to the length of our path. So we're going to rule out any paths that take this sort of movement. Similarly, if we ever move in the opposite vertical direction as our point, we're going to unnecessarily add to the length of the path. So we're also going to rule out this. So to take the shortest possible path, we're going to restrict ourselves to only ever moving in the same horizontal and same vertical direction as the point we're trying to get to. An easy path that only requires these movements would be one where we travel our full horizontal distance needed and then our full vertical distance needed. The length of this path is going to be equal to the absolute value of x1 minus x2, which is the difference in our x values, plus the absolute value of y1 minus y2, the difference in our y values. We could also use these movements to take a path like this with a few more turns in it. However, since we're only ever making 90-degree turns and we're only ever moving horizontally and vertically, we can actually see that the sum of our vertical movements and the sum of our horizontal movements are the same as they were for the previous path. That is, the length of this path is still the distance between our x values plus the difference in our y values. In fact, any path that only uses these movements is going to have the same length. The length of this path is equal to the length of this path, which is equal to the length of this path, and we can continue on and on and on and on until we get to a path that looks like this. We can think of this as being a path with an infinite number of turns, but we're still only ever moving horizontally and vertically. Thus, the length of this path, which looks diagonal, is still equal to the difference in our x values plus the difference in our y values. So now we arrive at an equation. If we want to figure out the length of the shortest path between points x1, y1 and x2, y2 in this new geometry, which we'll now call Taxicab, the length of this path is going to be equal to the absolute value of x1 minus x2 plus the absolute value of y1 minus y2. In other words, the length of any shortest path will be equal to our total x displacement and our total y displacement. Here's two examples of how we could apply this equation to find the shortest distance between 2 points. Now for an interesting question. What does a circle look like in this geometry? Let's set the center of our circle to be the origin of the Cartesian plane, which is point 0, 0. And what we're going to try to do is find all points that are r distance away from the center, where r is our radius. To knock out some easy ones, we can travel r units in any of our 4 starting directions and get a point that works. In Euclidean geometry, the equation for a circle is x squared plus y squared equals r squared, and would look something like this. However, if we take a point that would be on this circle normally, and we calculate the distance between the origin and that point, we don't get r. Thus, we're throwing this whole thing out. Instead, to construct a circle, let's go back to our distance equation. The distance between any point x, y, and the origin is going to be the absolute value of x plus the absolute value of y. So let's set this equal to our radius r and use known properties of absolute values to construct our circle. For quadrant 1, where x and y are both greater than 0, we get x plus y equals r, and we can do the same for each quadrant and arrive at our circle. Every point in the shape is r units away from the origin, so this is a circle with radius r and center O. In Euclidean geometry, we would consider this shape to be a square, but in Taxicab, again, this is a circle. So here's a comparison between a Euclidean circle and a Taxicab circle. We have our equations for a circle with a radius r and center hk in each geometry off to the left. And on the right, we have a graph of each, where we've set the center equal to 2, 3, and our radius equal to 4, and graphed a Euclidean circle in blue and a Taxicab circle in red. An interesting thing to note is that a rotation is no longer an isometry in this geometry, at least rotations as we know them. If we take our circle, centered on the origin with a radius of 5, and we rotate it 90 degrees, we don't get a circle anymore. We can see that the corners of this shape in blue off to the right are farther away from the origin under the Taxicab distance formula than any of the other points along the side lengths. Now for a final question. What is pi equal to in this geometry? We can figure out the perimeter of this circle by figuring out the length of each side, which ends up being 2r for each side. The circumference of a normal Euclidean circle is 2 pi r, and the perimeter of a Taxicab circle is 8r. So if we set these equal to each other, we arrive at the very unsettling conclusion that pi is now equal to 4. Anyways, thanks for watching.